Hi, today we're talking about Chapter 10, Section 3, Properties of Trig Ratios, or Trigonometric Ratios. This is one of the sections that I don't necessarily love because it requires memorizing some of these equations. I'm going to go through and try to show why they are. That's a lot easier for me if I understand why, as opposed to just trying to memorize weird random stuff. I want to start out just with a right triangle, so I draw one of those in your notes. And I'm going to label the sides A, B, and C. And kind of doing that somewhat discriminately. If you label your A, B, and C the same as mine, it'll make the notes a whole lot easier. And then theta, we said, was just a variable, kind of like an x or a y, but it's a variable that stands for an angle. So if we start out with a triangle that looks like that, and then from there I just want to say, well, what would sine of theta be? So sine of theta. So if you think back to before, we talked about SOHCAHTOA, and so then the S represents the sine. So sine of theta equals O over H, so the opposite leg over the hypotenuse. So our legs are A and B, the opposite leg then is going to be B, divided by the hypotenuse, which is letter C. Next thing I want to look at then is, well, what about this angle over here? What could we say about this angle? Well, we know all the angles of a triangle add up to 180. So if you take 180 degrees, take off the 90 degrees for the right angle, then these two angles here have to add up to 90. So you could then say, if you wanted to, this angle has to be 90 degrees minus theta. So that gives us what this angle would be. And now I'm wondering, well, if we were to talk about this second angle here, so instead of theta, I'm going to say 90 degrees minus theta. Well, what of that is also going to equal B over C? Is it sine? Is it cosine? Is it tangent? So for this angle over here then, B is the adjacent leg. Maybe I should write out my ka and my toa. So if we have B on the top, we're really looking at what's the adjacent over the hypotenuse, which then ends up being this ka. That cosine of this angle here is going to equal the adjacent leg B over the hypotenuse C. So what we just found is the first thing, which they refer to as the complements theorem. Now switch over to red. So here's two of the properties. So first thing you could write is that sine of theta, which for our triangle we found equals B over C. B over C is here. So then sine of theta has to equal cosine of 90 minus theta. I'm going to write 90 degrees minus theta. And the reason they call it the complements theorem is that complementary angles are angles that add up to 90. So these two angles here add up to 90. They're complements of each other. In the same way, we could go through and we could have done that same thing with cosine of theta. And cosine would be A over C. Then if we do sine of my new angle, 90 minus theta, that's also going to be A over C. So the other one then is cosine of theta equals sine of 90 minus theta. Or in layman's terms, if you're talking about the two acute angles of a right triangle, sine of one of the angles is going to equal cosine of the other acute angle of the right triangle. So that's going to be my first one. My second one that I want to look at, this usually shows up on the ACT somewhere. This complements theorem often is on there. This next one, pretty much always on the ACT, you're going to find one question like this. So you could say sine of theta. So sine of theta, let me redo my theta. Sine of theta, quantity squared, plus cosine of theta, quantity squared, equals 1. And for that, if you look at the reading in our book, section 3, there is a proof for this one here. There's actually a cooler proof in the notes that we're going to do tomorrow, 10.4. So I'd check that out for sure in the notes tomorrow. But this one here is usually going to be on the ACT somewhere. I probably should include the disclaimer, I'll put that in green, that this one here is going to be true for theta, so whose members are theta, such that 0 degrees is less than theta, which is going to be less than 90 degrees. And that's usually not a big deal, but this is going to be true for angles that are less than 90 degrees. And that'll also make a little bit more sense when we look at the proofs for tomorrow. Another one is going to be tangent. That when we talk about tangent of theta equals the sine of theta divided by cosine of theta. And this one sometimes shows up on the ACT. It's definitely not nearly as popular as the one with the squares up above. But if we wanted to kind of look at y, so I can freeze that there. If we were to look at this, so you could write this down if you want to, I just find it interesting. But when you have tangent of theta, if we pick my angle here, tangent is the TOA, so it's going to be opposite over adjacent. So I'll write tangent of theta equals opposite, so B over adjacent A. Well, if we were to do that same thing, say sine of theta over cosine of theta, so now sine of theta is going to be opposite over hypotenuse, that's B over C. So we have B over C in the numerator, divided by cosine of theta, so cosine's adjacent over hypotenuse, so A over C. And then for those, if we take that, dividing two fractions is the same as multiplying by the reciprocal. So B over C divided by A over C is the same as B over C times C over A. And now once we're there, we could cancel out the C's, leaving us that sine of theta over cosine of theta is just B over A, which then is the exact same as tangent of theta. So a quick little, I don't know if you really call that a proof, but quick little explanation, something or other. Alright, last thing, 3 things to memorize. And this used to be more important on the ACT back before they let you use calculators for it. Nowadays it does come in handy, and you will get some questions about this in my class. And again, this will also make a little more sense in the 10-4 notes. But there's 3 different trig ratios that you should memorize. One is going to be the sine of 30 degrees. And the nice part is if we know sine of 30, that's going to be the same as the cosine of what angle? Well, it'll be 90 minus the 30. So sine of 30 degrees is the same as cosine of 90 minus 30, or 60 degrees. And that one's going to be 1/2. So that's one to memorize. Another one is going to be sine of 45 degrees. And that'll be the same as the cosine of 90 degrees minus 45. So ends up being cosine of 45 degrees. And that's going to be square root of 2 over 2. And then the very last one would be if we're doing sine of 60 degrees, which will be the same as cosine of 90 minus 60, so cosine of 30 degrees. And that one is square root of 3 over 2. So that's it for this section. Those are 3 things to memorize there. Like I said, these come in handy on the ACT. They'll also come in handy as you do some work. Nice part about this is, as opposed to normally you punch in your calculator, you get a decimal approximation. These 3 things here, particularly these last 2, you get an exact answer instead of a rounded decimal. That's all for section 3.